Okay, so with all that stuff about inverse functions behind us, now we can talk about exponential functions, right? And we're going to start with the natural log function. And, just to remind you of the way we defined the natural log function, we defined it as a definite integral, right? It's the integral from 1 to x of 1 over t dt. Okay, so that's the definition of log x. And I want to clarify that, right, this x has to be positive. X has to be greater than 0, right? And if you remember, one of the properties of this function is that it is an increasing function. In fact, if you just draw a very quick graph of this, the graph looks like this, right? And it has a vertical asymptote, x equals 0. Yeah, it's continuing down this way. And so, yeah, it's definitely an increasing function on its domain. It's always increasing. And one of the things we said about that is if a function is always increasing, then it's 1 to 1. Right? So this natural log function, natural log of x, is 1 to 1. Right? After all, it satisfies the horizontal line test. Draw any horizontal line, it's going to cross only once. Right? Even the x-intercept, right? So, yep. Natural log function is 1 to 1. It satisfies the horizontal line test. Every horizontal line crosses the graph at most once. All right, so why do we care if it's 1 to 1? Well, we care it's 1 to 1 because now we can find the inverse. We're going to find the inverse of the natural log function. So step 1, we're going to write y equals natural log of x instead of f of x, right? And maybe, if you remember, natural log of x is really just the logarithm base e. So I'm going to write it that way, even though we usually write it just ln, right? Step 2, remember we switch the x's and y's. So just change y to x and change x to y. And step 3, we have to solve for y, right? So if log base e of y is equal to x, then what's y going to be? Yep, you should know this, right? You should know this. We're just finding the inverse, right? We're solving for y here. Okay, so yes, hopefully you're not dividing by log base e. You know not to do that. Instead, you kick the e to the other side, knocking this x here into the exponent. So when you solve for y, you get e to the x, right? And so that's the answer, right? So if f of x is natural log of x, then the inverse is e to the x. Okay, so this is our generic exponential function. And if you remember, this e here is approximately 2.71828. I think we talked about that, right? So that's just the base of the natural exponential function. Now, what happens if you have, like just 2 to the x, right? Or 7 to the x, right? Or 10 to the x. So yeah, we can talk about different bases. We'll do that later in the next section, in 5.5, I think. But for now, we're going to stick with e for the time being and discuss some of the properties of this exponential function. And I think I'm just going to copy them down for you and discuss them one by one. Okay, so here's some important properties. First of all, this I'm just to reiterate what we already said here, that it's 1 to 1, or the natural log function is 1 to 1, and therefore it has an inverse. And I went through it step by step. The inverse is e to the x, which is right here, right? And then this is sort of just how to convert from exponentials to logs and vice versa, right? So that you should know. What's the domain of this function? The domain of e to the x is all real numbers, right? And its range is all positive numbers. And you get that just from if you remember the original function, I'm calling them both f here. Maybe that's bad. This is f inverse. So f of x is log x. And if you remember, the domain of log x is all positive numbers, right, from 0 to infinity. And the range was all real numbers. So we talked about that in 5.1, right? So when you're finding the inverse, then you switch the domain and range, right? And so that's how you get that, right? What else do we know? We know it's also a continuous function, right? Because log is continuous, so is its inverse. Log is differentiable, so is its inverse. And of course, it's also increasing and concave up. Now, the concave up part, that might not be clear because the natural log was concave down, if you remember. So how do we get that the inverse is concave up? Well, we'll see that later when we take its derivative, right? We also have these two limits here. As x goes to negative infinity, you get 0. If you go to positive infinity, you get infinity. And, you know, I'm going to do a very, very rough graph here. So first, let's graph the log function one more time. The log function looks like this. So that's natural log of x. And now the exponential function is going to look like this, right? So that's your e to the x. So you can see when you go to the left, right, you have a horizontal asymptote y equals 0, but when you go to the right, it just continues to increase. So looking at the graph, of course, you can see why it's concave up. But yeah, that has to do with the second derivative. And we didn't even take the first derivative yet, right? So before we take the derivative, one more property. For any real number a and b, we have these two properties, which I hope you know by now. These you just got from algebra, right? It's just the product rule and quotient rule for the exponents. So these are just the usual rules of exponents here. Rules of exponents. So I'm not going to discuss them any further. You know, go back to your algebra book and they'll explain this, you know, quite profusely. But I'm assuming you understand these, right? And obviously this is not just true for E, but maybe I will remind you of the generic version of this, right? That if you have x to the m times x to the n, this is just x to the m plus n, right? So that's property 1 here. And then property 2 just says that if you have x to the m divided by x to the n, that's just x to the m minus n. So here they're applying it specifically to when x is equal to e, and they're changing m and n to a and b, but it doesn't matter, right? So again, these are just the rules of exponents. And that's all I'm going to say about that. Okay, now we can get to the derivative. All right, so we have our original function here. All right, hang on. All right, so f of x, well, okay, it's f inverse of x, right, is e to the x, but it's just another function, so we can call it g if you want. I'm just going to call it f from now on. Okay, so it's just some function, e to the x, and we want to take its derivative. All right, what is the derivative of e to the x? And again, some of you might know this already. Most of you probably don't. So we're going to figure it out by going back to this property here. Right? Yep, we're not done with this yet. So we just did this in section, in the last section, 5.3, talking about inverse functions, right? Yeah. So actually, I do take that back. We are going to call this f inverse now. So this is going to be the derivative, oh boy, of f inverse. Okay, where f of x, so what's f of x? F of x was the original function, that's the natural log of x. Okay. Actually, I take that back. Instead of using this, which I know some of you are still trying to absorb and trying to make sense of this, You know, we did a couple examples in the last video, but I get the sense that this is rather tricky. So instead of using this property directly, here's what I'm going to do, right? We're gonna express the following fact, that if you take f inverse of f of x, you just get back x, right? Or I think in this case, so if f is the log function and f inverse is e to the x, then we want to apply this version, f of f inverse of x equals x. Right? So what does that say here? It says that if we take the natural log of e to the x, right, we just get x. Okay. This version up here just says that if you take e to the natural log of x, you also just get back x. Of course, here this is for positive x. This is for any x. This is true for any real number x. Okay, so what are we going to do with this here? Right. So again, I'm hoping you understand this as just expressing the fact that the log and the exponential are inverse functions. So here's what I'm going to do. I'm going to take the derivative of both sides. So implicit differentiation. I'm going to take the derivative of the left side, and I'm going to take the derivative of the right side. I'll let you do the derivative of the right side. I'll take care of the left side. Yeah, I mean, I gave you the easy one, right? The derivative of x, of course, is just 1, right? dx over dx is 1. Right, so now, let's look at the derivative of the left side. Well, again, way back in section 5.1, was it? Yep, I think it was in 5.1. Actually, it was 5.2 officially. We talked about, right, the derivative of log x, and that was just 1 over x. Actually, that was 5.1. I take that back. It's 5.1. And we did have the absolute value here as well, but we don't need it here. We're assuming that x is positive, right? So this is for x positive here, right? Yeah. However, this is not the log of x, it's the log of e to the x. In other words, it's the log of a function of x, say g of x. So that's 1 over g of x, and then by the chain rule, the numerator is g prime of x. So putting this all together, maybe I should do this here. Putting this all together now, we want to take the derivative of the log of e to the x. So my g of x here is just e to the x. So we want the derivative of e to the x divided by e to the x. Now, you might think, well, wait a minute, that's the question, right? The question is, what is the derivative of e to the x, right? That was this big question mark up here. Well, hang on, right? Hang on to that thought, because this is the left side of the equation here. So I'm just going to copy this down. In fact, I'm going to write it this way. This is just 1 over e to the x times the derivative of e to the x. So put that over here. 1 over e to the x times the derivative of e to the x. So you see what to do, right? I'm solving for this. So I have 1 over e to the x on the left. So how do I cancel e to the x in the denominator? I just put it in the numerator. So I multiply the left side by e to the x. So I have to multiply the right side by the same e to the x. And when you do that, on the left, they cancel. And on the right, well, now we have our answer. The derivative of e to the x is 1 times e to the x. The derivative of e to the x is e to the x. It's a function whose derivative is itself. Okay? So this is kind of weird, right? Up until now, we've never had a function whose derivative is just itself. When you take the derivative of a function, you get something else, right? You don't get x squared again. Although there is the trivial one. Of course, if you take the derivative of 0, you still get 0 because it's a constant, right? But that's almost too easy, right? That's boring. Here we get a non-trivial function, e to the x, whose derivative is itself. Okay? So going back up here, that we were answering this question. What's the derivative of e to the x? And now we have our answer. It's, well, maybe a little surprising, but it's also just e to the x, right? So there you go. The derivative of e to the x is e to the x. So hopefully that's not hard to remember, right? That's one that's probably pretty easy to remember. And you might want to remember the chain rule version. If you take the derivative of e to the u, that's just e to the u, but don't forget to multiply by the derivative of u by the chain rule. Okay, so some examples. Well, let's start with find the derivative of, how about f of x equals e to the tangent x. Okay, so we want, the derivative, I'll write it this way, the derivative of e to the power tangent x. So tangent x is the exponent of e, right? And going back up here, that's my u, right? That's my g of x, if you will. That's my u. So according to the chain rule here, the derivative of e to the x is e to the x. So the derivative of e to the tangent x is e to the tangent x. Looks like tanks here. So tangent of x. But you can't leave it like that because there is a chain rule. We have to take the derivative of the exponent, the derivative of tangent x, by the chain rule. And I'm hoping you remember the derivative of tangent x, none other than secant squared of x. Okay. So yeah, not a hard one, but it's one that if you forget the chain rule, right, you're going to forget the secant squared of x parts. Right. So I'll let you think about this one. This will be example 2. Find the derivative of e to the, okay, I'll make it pretty easy, right? E to the 3x minus 4. Right, so 3x minus 4 is the exponent of e. Yep. So, yeah. Okay, hopefully you got it. This is just e to the 3x minus 4 times the derivative of 3x minus 4, which is just 3. And we should really bring the 3 in front. It looks better like this. So 3 times e to the 3x minus 4. Okay. Yep. So not hard. Let's do another one though. And let's do one that involves some application of the derivative. Let's find the absolute minimum value of the function, so we'll call it f of x, and let's make it x times e to the x. Okay. So first of all, it's not a trick question, right? Does it even have a minimum value? And I assure you it does. It does have an absolute minimum value here. And yeah, we want to find that minimum value. Right, so first thing to note is that the domain is all real numbers, right? So this is, this is all real numbers for the domain. X can be positive or negative, right? And so can the exponent. So the next thing we want to do is, what do we mean by absolute minimum? Well, the graph comes down and goes back up, right? Something like this. So where are you going to have a minimum add a critical number, right? Remember, critical number is where the derivative equals 0. The slope of the tangent line is 0. So how do we find the derivative? Well, we take the derivative, right? How do we find the critical numbers? We take the derivative and set it equal to 0. Now, you might say, well, how do you know it doesn't do this? It comes to a corner. Well, that's if this were not differentiable. And you'll see in a minute when we take the derivative, this will be differentiable for all x, right? So no corners, no cusps, nothing crazy here. Right. So, yep, let's just take f prime of x, right? So we want to take the derivative of x times e to the x. Well, I hope you realize we need the product rule here. This is not 1 times e to the x, right? It's first times the derivative of the second plus second times the derivative of the first, right? The ordinary product rule for derivatives. Right? Now, what's the derivative of e to the x? Oh, I shouldn't do that here. Right. What's the derivative of e to the x? Well, we just said that. It's e to the x, right? Hopefully you can remember that. So, so this first term here is x times e to the x, right, plus, and then e to the x times the derivative of x, which you should know that by now is 1. So we get x e to the x plus 1 e to the x. And we can leave it like that, or notice we have a common factor of e to the x. We can factor it out and write this as e to the x times x plus 1. Right? You don't have to, but trust me, writing it this way will be much more helpful. Right? Because remember what we wanted to do, right? We want the derivative. We want the slope of the tangent line. This red line here has slope 0 because it's a horizontal line. So we want to find the critical numbers, right? We want to take the derivative and set it equal to 0. So here's the derivative. It's e to the x times x plus 1. When does that equal 0, right? We have to solve this equation now. So I'll let you do that. It's not hard. After all, there's two factors, right? So there's two possibilities. You get either that e to the x equals 0, or you get that x plus 1 equals 0. Well, this you can do in your sleep. This is just x equals -1. Right? So that's one solution, x equals -1. What about this equation here? How do you solve that? Right, you can't. It's not equal to 0, right? If you were to convert this to a logarithm, you would get that x is the natural log of 0, which is undefined, right? So e to the x will never be 0. E to the x will always be positive. Yeah, I'm running out of space here, but I think I have enough space to write that. E to the x, that's the range of e to the x. It's greater than 0. It will never equal 0. So yeah, there's no equal sign here. E to the x is never 0, right? So yes, right. So this is out, meaning there's only one solution, and that's this -1, which, you know, it should have been obvious, right? You could have divided both sides by e to the x because it's never 0. Okay, so there's our critical number, right? You solve this equation and you get x equals -1, right? And there's only one critical number, so it better be a minimum. Right? No, as I said, no trick questions. It's not going to be a maximum. So if that's the minimum, how do you find the minimum value? Well, that's the y-coordinate, right? So now we have to plug in, I should do this here, into the original function, we should plug in -1. So here was the original function. This is just going to be -1 times e to the -1. Or you can write it as -1 over e. And that's the absolute minimum value. Right? It's approximately -0.3679. right? So it's about negative 1/3, but it's actually a little bit less than that. But that's the absolute minimum value, and it occurs, right? It occurs at x equals -1. So this is a pretty poor graph up here, but I can do slightly better than that. So here's -1. So the graph actually looks like this. It's going to go down, and then at -1 it levels off, right? And then it just increases from there. Right? So you do get a relative minimum and an absolute minimum, right? It's both a relative minimum and an absolute minimum. And x is -1 and y is, well, -1 over e. And it is negative, right? It does have an x-intercept at 0 here because, well, if x is 0, right, remember e to the 0 is 1, so you get 1 times 0 is 0. So, yep, it does pass through the origin. In any event, that answers the question, right? Find the absolute minimum value. The answer is -1 over e, to be exact. Of course, you can also get the approximate on your calculator, but again, we want the, I should have mentioned, the exact absolute minimum value. Okay. All right, so I'm going to clear all this because we did a lot here. Boy, we really did a lot. So let me clear this, and then we'll come back and do one more important property. Okay, so we know that the derivative of e to the x, right, is just e to the x. So now we want to talk about finding the integral of e to the x dx. Right, and so you shouldn't have to think too hard about it. After all, if the derivative of e to the x is e to the x, when you go backwards, the integral of e to the x is, yeah, same thing, e to the x, right? But this is indefinite integral, so don't forget your plus c here. That's, right, that's important. And yeah, we also might need to do a substitution. So don't forget the integral of e to the u du is just e to the u, right? And I know in this case you're just changing x to u, but that's, that's not trivial because in some problems u might be, 5x minus 3 or something. In fact, let's do that as our first example. Right? Let's evaluate the indefinite integral of e to the power 5x minus 3. Right? So, in other words, the exponent is 5x minus 3, right? Well, how do we do that? So, pretty clear that if this is the exponent, I need the exponent here, this 5x minus 3, that has to be my u. No choice here, right? So what's du? Du is, well, the derivative of 5x is just 5 minus 0 times dx, right? Now, notice I have a dx. I don't have a 5, but that's not a problem. 5 is a number. It's a constant. I can multiply by 5 as long as I also divide by 5. And just for convenience, it might be better to divide by 5 on the outside, right? So I did that in order to change this into, right, du. Right, so that becomes my du. So I just get 1 over 5 times the integral of e to the u du. And, well, there you go, right? The integral of e to the u is e to the u plus c. Don't forget the 1 over 5 in front. And don't forget to change u back to 5x minus 3, right? Because that was the exponent. So we get 1 over 5 times e to the 5x minus 3 plus c. Right. So, yep, not a crazy hard one, but but it does use substitution, right? So yeah, you have to be careful. You can't just say that the integral of e to the 5x minus 3 is e to the 5x minus 3, because then you'd be forgetting the 1 over 5, which comes in from the substitution, right? This 1 over 5 here. Okay, so that's how the integral of e to the x works, and maybe we'll do a couple more. Yep. So how about if we evaluate, let's do the integral of e to the sine x times cosine x. Okay. Again, this one's not supposed to be that difficult. I can see three different possibilities here, right? Obviously, this is a product, and there's no product rule, right? No product rule for integrals. So what should u be here? Let me scroll down a little bit here, because it's clear we have to do some sort of a substitution here, right? Well, your choices are as follows. You can let u be cosine of x, right? That's one possibility. You can let u be e to the sine x. That's another possibility. But I think the simplest one, and the one that worked in the last problem, is that the u is the exponent. In other words, u is just the sine x by itself. So let's try that. U is just sine x. What's the derivative of sine x? Of course, it's cosine x, right? So my du is just cosine of x times dx. And hey, look at that. We have that exactly here. So this is just my du. This is just e to the u. So we get the integral of e to the u du. And hopefully you haven't forgotten that yet. But here it is again. Right up here, this big thing here. Yep, so that's the integral of e to the u is just e to the u plus c. But don't forget to change this back. U is what? U is sine x. So this is really e to the sine x plus c. Okay. Hey, we should check, right? We haven't been doing that. Well, we haven't done it enough, right? We should have done it here too, obviously. But let's check, right? If I take the derivative of e to the sine x, right, plus c is a constant, right? What do I get? Well, the derivative of c is 0 here, right? But what's the derivative of e to the sine x? Well, it's e to the sine x, right? And then don't forget the chain rule. We have to multiply by the derivative of the exponent, the derivative of sine x. Well, the derivative of sine x is cosine x. And that was the integrand, right? That was the thing we were integrating up here, e to the sine x times cosine x. So there you go. We have the correct answer. It's always good to check, right? So yeah, when you're doing a substitution, when you check your derivatives, you are using the chain rule here. Right? So that, remember, the chain rule is reverse substitution. We have a chain rule for derivatives, but for antiderivatives, we have substitution. Okay. I hope that helps. I think we can do one more. I'm running out of space, but I don't think this one will be long. So let me put up the problem, and then we'll see how we can do that. Okay, let's do a definite integral. This is the definite integral from 0 to 1 of e to the x over e to the x plus 1. Okay, so this one's a little trickier here. Right? So yes, the integrand here is a fraction. It's a quotient. So we apply the quotient rule, right? But this is an integral. There is no quotient rule, right? No quotient rule. So I was trying to trick you there. There is no quotient rule, right? For derivatives, yes. But this is not a derivative. This is an antiderivative, integral. right? Definite integral. So what do we do? If there's no quotient rule, we try the only thing we know how is substitution. So what should u be here? Well, it could either be the numerator, e to the x, or the denominator, e to the x plus 1. Now, so if you try this, you'll see it doesn't work because the du is still e to the x, but that will not take care of this e to the x plus 1. So that doesn't work. So, yep, it's going to be the denominator. U is going to be e to the x plus 1. Because the derivative of that is still just e to the x plus 0, right? Because the derivative of 1 is 0, dx. So if we rewrite this as the definite integral from, sorry, that was supposed to be a 0 here, 0 to 1. And let's write it this way, e to the x dx in the numerator divided by e to the x plus 1 in the denominator. E to the x and then plus 1, right? The plus 1 is not in the exponent, right? This is not e to the x plus 1, right? The plus 1, I hope it's clear that, right, the plus 1 is outside of the exponent here. Okay. All right, so what do we do here, right? So this is going to be our u in the denominator here. This is going to be u, and this is going to be du, right? So we can rewrite this as the definite integral du over u. But I hope you're not tempted to do 0 to 1 because that's wrong. All right, remember, these are x's here. So let's calculate this. Let's calculate the u's. All right. If x is 0, then what's u going to be? It's going to be e to the 0 plus 1. But e to the 0 is 1, and 1 plus 1 is 2. So if x is 0, right, then u is equal to 2. Right. Now, what about the upper limit when x is 1? So if x is 1, then u is going to be, well, e to the 1 plus 1. Now, e to the 1 is just the number e plus 1. But that's the best we can do, right? Let's just leave it as e plus 1. E plus 1, right? Or 1 plus e, same thing, right? I mean, look, it's approximately 3.71828, but let's not do the approximation yet. Suppose we want the exact value. In fact, it'll say that on the test, right? Evaluate and find the exact value. So no approximations. We can do that at the end if we want, but right now we want the exact value, right? So yeah, this is also u here, right? And by now you know full well what the integral of du over u is. Yeah, let's pause to think about that, right? This is the exception to the power rule, right? This is going to be the integral of u to the negative 1, which is not u to the 0, right, divided by 0. It's natural log of absolute value of u plus c. Right? So natural log of absolute value of u. We don't need the c here because this is a definite integral. We need to plug in, oops, not the 1 here, but the 2 and the 1 plus e. E plus 1. I'll leave it as e plus 1. E plus 1, right? So, yep, this is just a fundamental theorem of calculus, right? You have the natural log of the absolute value of the top minus the bottom, right? And these are, right, we know that 2 is positive, obviously, and e plus 1 is also positive. Obviously, it's bigger than 1, but it's also bigger than 0. So we don't need absolute value here, right? We can just write it as the natural log of e plus 1 minus the natural log of 2. Or better yet, hopefully you remember this property, right? If you take the natural log of a minus the natural log of b, that's the same thing as the natural log of a divided by b. So we could write this more succinctly as the natural log of e plus 1 over 2. And yeah, maybe I kind of prefer that. instead of this. Although, to be fair, I'm not going to be picky, right? This is correct. There's nothing wrong with this. But when you can combine them into a single log, that's probably better. Okay, well now, if you want, you could plug this in your calculator, and this is going to be approximately 0.6201. Right, so yeah, like I say, you could have done this directly on your calculator from the beginning, but that would have only gotten you the approximation. But here we want the exact value, which is, oh boy, squeeze it in here, natural log of e plus 1 all over 2. Okay, so, yep, so that's how to do an integral with e to the x and a substitution as well. Okay, so, yep, I guess we'll do another. Okay, so here's another example. We want to find the equation of the tangent line to the graph of this thing here, right? 1 plus log of xy equals e to the x minus y at the point 1, 1, right? So at a specific point, you know, the graph will be some, well, I have no idea what the graph looks like. That's not the point, right? But we have some equation of some graph here, and we have at the point 1, 1. And presumably we have a tangent line, and we want to find the slope. Well, we want to find the equation. So, yep, if you remember, to find the equation, we need the point, which is, well, 1, 1. Right, so that's my x0, y0, so we can do that right now. Right, yep, x0 is 1, and y0 is 1. But in order to find the equation, we need m, we need the slope. And it's a tangent line, so we don't know any other point on the line. That's the whole idea, right? This may cross somewhere else, but it may not. So we have no way of knowing any other point on this line other than the 1, 1. That's the only point that they give us, right? I mean, obviously, if they gave us 2 points, well, then that's a very easy problem, right? So, no, obviously, to find the m here, right, to find m, we're going to have to take the derivative and then plug in x equals 1 and maybe even y equals 1. Okay, so, yep, that's the key. How do we find the derivative? Well, you could try solving for y here, but notice there's a y on both sides. And if you try to do that, you're gonna start pulling your hair out because it's not easy. And in fact, I don't see a way to do it. So I wouldn't know how to do that, right? What is y in terms of as a function of x? No idea. In fact, there may not even be a function, right? And I'm guessing this might not even be, 1 to 1. So this might not represent a function. It might be just a relation of some kind. Okay, so we're not going to be able to find y explicitly as a function of x. However, we do have implicit differentiation, right? We can just take the derivative of both sides. We've been doing that quite a lot, right? We've done that quite recently. So, yep, just take the derivative of the left side and take the derivative of the right side. All right. So let's do the left side first. The derivative of 1 is 0. That's easy. And what's the derivative of log of xy? Well, right, this is the derivative of log of u, which is 1 over u, or 1 over x times y. But don't forget there's also a chain rule. We have to take the derivative of x times y. Okay. So, yeah, maybe we should do that now, right? Before we do the right side, we'll do that later, right? Let's do this. So 0, we don't need the 0 here. This is 1 over x times y. And what's the derivative of xy? Well, yeah, it's a product, right? We need the product rule. So I hope you're not doing 1 times the derivative of y. Nope. It's going to be x times the derivative of y plus y times the derivative of x. But the derivative of x, of course, is just 1. So we get 1 over xy times x times the derivative of y plus y. Again, derivative of x is 1. So running out of space here, but let's distribute the 1 over xy. So we get x over xy times the derivative of y plus y, plus, not equals. This is a plus, y over xy. Well, in the first term, the x's cancel. In the second term, the y's cancel. And so we end up with 1 over y times the derivative of y plus 1 over x. Okay, so that's the left side. Now what's the right side? So what's the derivative of e to the x minus y? Well, pretty easy, e to the x minus y, right? But again, there's also a chain rule. So now we have to take the derivative of x minus y, that's the exponent, right? But that's easy. This is a difference, so you just apply the sum rule or difference rule. We get the derivative of x is 1 minus the derivative of y, which is, well, the derivative of y. That's what we're looking for, right? So that's, I think, the best we can do. I'm just going to pull that all the way down here now. And I think, unfortunately, I have enough room here. So this is not going to be easy, because at this stage here, we have to solve this for the derivative. Solve for the derivative of y. Okay, so let me just write this a little bit more neatly so we can do this solving here. Right? I mean, we did the calculus part, right? We took the derivatives. Now we just have to do the algebra. Right? We're solving for the derivative of y here, right? Okay, so let's see how we can do that. Yeah, I'm not even sure we can do that. Well, okay, so I guess what we'll have to do on the right here is multiply this out. So I'm going to leave the left side alone for now. I'm tempted to write this as y prime, but I'll leave it. So this is just e to the x minus y plus e to the x minus y times the derivative of y. So, okay, so we did that. So now we need to take this term with the dy over dx to the left side, because we want all the dy over dx on the same side. I mean, we could pull this on the right, but I'd rather have it on the left, right? So the left side is going to become, 1 over y times the derivative of y, and then minus e to the x minus y times the derivative of y. We still have the 1 over x on the left, and then the e to the x minus y on the right. So I think it's pretty clear now. We just want to subtract the 1 over x from both sides. And if we do that, from these two terms, let's factor out the dy over dx. And then on the right, we get e to the x minus y minus 1 over x. So now all we have to do is divide both sides by this factor here. Right? This is 1 over y minus e to the x minus y. Do it on the right. Well, okay, I'm writing it backwards here, right? But that just means you multiply by -1. So, yep, that's just to make it look right here. So these cancel, and now we have our answer. We have the derivative of y equals, pull the negative in front here. It's going to be a negative fraction, e to the x minus y minus 1 over x over e to the x minus y minus 1 over y. And, well, that's quite a mess. And in fact, you have fractions within fractions, but I don't think that really matters here. If it really bothers you, you can just multiply top and bottom by xy. Right. Not necessary, but just to simplify, right? So you're going to get, let's see, xy e to the x minus y minus, the x's cancel, so this is minus y here. And then in the denominator, you're going to get the same thing, xy e to the x minus y, but this time minus x. Right. And if it helps, you can factor out the y in the numerator. And then factor out the x in the denominator. And you can see that these are awfully close here. It looks like you can cancel, but this is an x, this is a y. They don't match. So nope, nothing cancels here, right? All right, so there's our derivative. Oh, but that's not the question. Sorry, we're not done yet. The question is to find the equation of the tangent line. But in order to do that, right, we need the derivative here. Remember, we're looking for the derivative so we can get our m, the slope of the tangent line, right? And what do we need to plug in here? Just the 1 and the 1. So x equals 1, y equals 1, right? So going way down here, my m now is just going to be the derivative of y evaluated at x equals 1, y equals 1. So if y is 1, this is just going to be, well, 1 times, x, which is also 1, times e to the 1 minus 1, over 1 times e to the 1 minus 1, minus 1. And that looks pretty complicated, but, right, when you just multiply by 1, you just get that, right? And, oh, this is not good. E to the 1 minus 1 is e to the 0. But e to the 0 is 1. You get 1 minus 1 is 0. Oh, that's not good. Hang on. So I got to, 0 over 0 is undefined. Okay, let's think about this. Yeah, we should not be getting 0 over 0. Well, if that were the case, then there's no tangent line, right? Then the slope is undefined, which means there is no tangent line. And that could happen, but I don't think it happens here. So, all right, let's see here. So, obviously, there is a point here on the graph. If x and y are both 1, log of 1 is 0. So you get 1 plus 0 on the left, and e to the 1 minus 1 is 1, so 1 equals 1, right? So there is a point on the graph here. So it should have a tangent line. It should have a tangent line. I got it. Typo. And some of you are probably screaming at the screen. Sorry about this. I found my little mistake here. This was a minus sign, and for no good reason, I changed that to a plus sign. So, again, a lot of you probably knew that. So that makes this a minus, and so I actually had to add this to both sides, right? So that means this becomes a plus here. And this, this is still a minus, right? So yeah, this was a minus, so we had to add this to both sides, not subtract. Okay, so that means, let's see, this is a plus, this is a plus, this is a plus. But then there's no negative 1 here, right? And there's no negative 1. Yep. So yeah, I got the wrong derivative. Okay, it's easy fix though. So ignore all this. So the derivative, let's just put that up here, should be e to the x minus y, that's an e, minus 1 over x divided by e to the x minus y plus 1 over y. Okay, so now when you plug in, well, I'll have to do it again, right? To get the slope, we're just going to take the derivative and plug in x equals 1 and y equals 1. And so the numerator is 0, but the denominator is not 0. The denominator, well, here, you get e to the 1 minus 1 minus 1 over 1, divided by e to the 1 minus 1 plus 1 over 1. So you get, e to the 0, which is 1. You get 1 minus 1 over 1 plus 1. Yep, you get 0 divided by 2, which is 0. So, yeah, because this was supposed to be a plus, yep, you get 1 plus 1. Sorry about that, but we do get a number. We do get 0 here, right? So the slope is 0. And now we can finish the equation. Sorry for using red here. I hope everyone can see this. But here it is again, right? Y minus 1 equals m times x minus 1. But if m is 0, 0 times, oops, sorry, that's supposed to be 1. 0 times anything is 0, and y minus 1 equals 0 tells me that y equals 1. So there's the equation of the tangent line, right? Y equals 1. So it's a horizontal line. So it turns out that this picture is a little flawed here. Yep, the point is going to be probably down here where the slope is 0. So you get a horizontal line with slope 0. And yeah, I'm glad I found my little mistake here. You know, yep, you can laugh, but I'm sure I'm not the only one that makes these little mistakes. We all do that. So it happens to the best of us, right? But, you know, I was able to fix it, and we got a legitimate answer here, right? So there is a tangent line, and it just happens to be horizontal, you know, which is pretty hard to tell just looking at the equation here, right? And again, don't try to graph this. It's not going to be easy to graph. Okay, so I guess that's it for 5.4, I believe this was. So yeah, exponential functions, and, you know, doing integrals and derivatives of exponential functions.